because we have the desired h of e power j omega function from n is equal to minus infinity to infinity. This sequence ht of n is our desired impulse response, but it is an infinite length sequence. In order to convert into infinite impulse response into a finite impulse response, previously we have taken h of n is equal to ht of n for the range of minus of n minus 1 by 2 to n minus 1 by 2, right? This was happened in the previously, because when it is happening, this hd of n total n number of samples are, suppose these are the samples, these are the samples, infinite number of samples. Because of this finite length we need to consider, we have considered only a finite set of samples, and remaining samples we neglected. So because of this, what happened? We have approximated this remaining samples with this finite length only. Okay, and with this abrupt change in the impulse response from this set of values, from the total infinite number of sample values to a finite length, there is an abrupt change in the frequency response. Because of this, this h of e power j omega filter response will produce some ripples in the pass band as well as stop band. So in order to avoid this ripples present in the stop band and pass band, we need to smoothly take the finite length samples from the infinite length. So that's what, how effectively you will take the samples, not shortcut of like this values and remove this rest of the values. You can take in different ways. So if infinite length of impulse response, impulse sequence can be made to finite length by multiplying a finite length sequence called a window. So this is a total sequence, and this total sequence is multiplied with a finite length sequence, right? Then the total will become a finite length sequence. Okay, now we will see this. What are these possible windows to reduce the infinite impulse response to finite length? Okay, this, while selecting this window window omega of n, we need to follow some set of properties. I mean, randomly we should not take the window sequence. We need to select the window such that it will satisfy some properties. One is one is this Wn is a symmetric. That means W of n is equal W of minus n, which is not equal to 0 for the duration of, for the duration for the duration mod n less than or equal to n minus 1 by 2. Okay. Okay, this is the first property. It must be symmetric about the origin, but this value should not be equal to 0. Okay, then next point is the Fourier coefficients, of course. The frequency response of this window. Frequency response. Frequency response of this window window sequence window sequence, that is W of e power j omega frequency response of the window sequence W of e power j omega must have a center lobe or central lobe that contain must have a central lobe that contain most of the energy and should be a narrow one, should be narrow. Okay, that means the frequency response, suppose if it is like this, so okay, this is the frequency response of a window. Suppose if you say this is called a main lobe or central lobe, main or center lobe, and these are called side lobes. Side lobes. Okay, so compared to the side lobes, the central lobe must have all the most of the energy of the W of e power j omega function, and this should be very narrow because in the filter this main lobe indicates the transition band. See, this is the low pass filter response, and here this is the pass band and this is the stop band. In the middle it is called transition band. Okay, basically this transition band should not be there ideally. So transition band should be very narrow, then only it will reach the this reaches the ideal response, correct now? Here see, the transition band is very narrow, so this part is very narrow. This is the pass band, this is the stop band. See this range between pass band and stop band, the band is very narrow. That is the narrow transition band. If it is narrow, then this side lobe width also will be narrow. So we want a narrow side lobe here, a narrow central lobe. Therefore, if it is very sharp like this, then it will provide a narrow transition band. Okay, that kind of window we need to select. And this side lobes indicates the ripples in the pass band and stop band. Therefore, this next property is side lobes. The highest side lobe, the highest side lobe should be small. Should be small. See, highest side lobe here it is this one, because if you take this response, it will keep on reduce it. Okay, so this is the highest side lobe. This highest side lobe must be a smaller amplitude. See, here it is very smaller amount. So that kind of response we need. If it is not there, see in this kind of response, see the side lobe is not at all visible. That means the side lobe amplitude is very small. So this kind of response basically will prefer it. And next, these side lobes, the side lobes of the frequency response should decrease in energy. Side lobes should reduce, should decrease rapidly in energy. In energy. Okay, from uh, as omega tends to pi. That means here, see, this is the first side lobe, this is the second side lobe, this is the third side lobe. So as the side lobes are increasing, that amplitude will be reducing, keep on reducing. So that means the energy is in the reducing order, in the decreasing order. Okay, these four properties must be satisfied. Of course, anyhow, the first is the selection symmetry. That is, always we will select a window like that only. But when it is coming to the frequency response, in the frequency response of window, these three property must be satisfied. Then only we will get our desired frequency response of the FIR filter. Okay. So whenever they asked what are the properties of a window, you can write these properties. Okay. Any doubt here?
No, sir.
Okay. Now we'll start. What are the different windows we have? Types of windows. Different types we have. We will see one by one here. The first window is rectangular window. Okay, let me first list out what are the windows, then we'll start one by one. First window is a rectangular window. Next one is a triangular window. Triangular window. Or this is also called Bartlett window. Bartlett window. And next third one is raised cosine window. Raised cosine window. And the next one is Hamming window. Hamming window. And next fifth one is Hanning window. Okay, Hamming is different, Hanning is different. Hanning window. And after that we have Blackman window. Blackman window. And next last one is Kaiser window. Kaiser window. Okay, so these are the 7 types of windows we have. We need to discuss each and every one. Here rectangular window will start, and to overcome small drawbacks in each window, slowly we'll go to the next different windows. Triangular windows, then raised cosine window, again Hamming Blackman windows. Then all these problems, whatever we faced in the previous windows, will be sorted out. Or the consolidated advantages of all other windows you can achieve from Kaiser window. So in most of the applications, if you ask me what is the best filter window in technique to design the FIR filter, I can say it is Kaiser window, because it you can tune easily the filter frequency response to your desired frequency response. That is possible in the Kaiser window very easily, and also you can achieve all these other windows using the Kaiser window. So for different applications, suppose one application rectangular window may be sufficient. Some other applications that is not suitable, so you can Hamming window may be correct. So in such a way, you can't every time change the window. So better use the Kaiser window or tune the parameters to achieve one time rectangular window shape and one another time is Hamming window shape. That way is possible in the Kaiser window. Okay, anyhow, we'll see one by one what are the features. The first one is the rectangular window. First one is rectangular window. Rectangular window. So what is the rectangular window shape and what is its frequency, and what is the frequency response side lobe and main lobe widths and all, we will check it now. So the rectangular window is defined as WR of n. It is not omega, it is WR of n. Small w for time domain and capital W for the frequency domain. So WR of n is equal to 1 for minus of n minus 1 by 2 to n minus 1 by 2. Else it is equal to 0 otherwise. Okay, that means the window in the graphical way it is shown like this. Suppose for n is equal to, it is from minus 5 to plus 5, center 0. Okay, 1 2 3 4 5, then middle sample, then again 1 2 3 4 and 5. So these are the all are having equal amplitude, that is equal to 1. So this is the WR of n sequence. WR of n sequence. This is n. This is rectangular window definition. For this window, if you apply the dt of t, will be having WR of e power j omega is equal to, after simplification, if you do simplification from n is equal to minus of n minus 1 by 2 to n minus 1 by 2, 1 into e power minus j omega n. If you do it, you will get, after simplification, similar way, you will get sine omega n by 2 by sine omega by 2. Sine omega n by 2 by sine omega by 2. If you simplify, you will get like this. So simplification is not required here, so I am not doing that. If you want, you can do practice, you will get like this. And from this, if you draw this frequency response of this omega versus this magnitude response of W of E of omega. Then what you will get when R is equal to this omega is equal to 0. At what value it will be 0 every time? When omega is equal to 0, this is equal to 0 only. So it is not defined. So that time we will apply the limit theorem. Then we will get some magnitude, highest magnitude value at omega is equal to 0. That already we know it. We have done in the previous problems. Then this WR of e power j omega is equal to 0 always, because at many values of omega you will get 0 because it is a sine function. We already seen these 0 values in the previous problem also. So this is equal to 0 when this point omega n by 2 is equal to, whenever it is equal to pi 0, pi, 2 pi, 3 pi and so on, wherever it is value you will get sine of this is equal to 0. Okay, so omega n by 2 is equal to k pi, where k is an integer. Wherever it is k pi, then this value is equal to 0. From this, omega is equal to what we can write? 2 pi by n into k. Okay, so wherever omega is equal to 2 pi by n into k, there this value omega WR of e power j omega is equal to 0. Okay, therefore wherever k is equal to 0, suppose k is equal to 0, means it is equal to 0, omega is equal to 0. So when omega is equal to 0, this value is equal to 0. And sorry, omega is equal to 0 means this is equal to 0. But omega k must be a non-zero integer. Is a non-zero integer, because whenever omega is equal to 0 here, by the limit theorem we are getting the maximum value. So that is wrong from this state, from this formula. So it is excluding 0. So k value must be greater than 0. Okay, at k is equal to 1. What is this? 2 pi by n. That means this is maximum at omega is equal to 0, and next value at 2 pi by n, this value is coming to 0. Okay, and next value, since it is a sinusoidal function varying from -1 to 1, it is having negative values also. Then again it is equal to 0, but at k is equal to again 3 pi by 4, 3 pi by n, and so on. Of course, the second values and all are not required. We are concentrating on the first lobe only. So leave it, and so on. It will be repeating always. Always it is repeating. Similar way, this side also at -2 pi by n, it is getting 0. Next, it is repeating same thing this side also. Okay, this is the frequency response of the rectangular window function. Do the table in the previous example kind and plot this, you will get a sinc function. Of course, from the DTFT properties directly we know the Fourier transform of a rectangular function will be a sinc function. So see, from the rectangular function we got the sinc, right? So this is the response, but what we have to observe is, what is this? Is the maximum energy is stored in the central lobe or not? So this is the central lobe. So in the central lobe, this total energy is maximum energy is placed, right? That is the first property. It is satisfied. Second property is the first side lobe of the frequency response must be a small one. So compared to this is very small only. If you, I think you can do it, you will get 1 by 2 n. I think n value you will get n is equal to 11 means here n is equal to 11 you will get here, but compared to 11 this value will be very very small. So definitely we will get a small value compared to this maximum value. Therefore, second property is also satisfied. Next, third property is as this omega is approaching towards pi, this value must be reducing. I mean, this amplitude values must be reducing. Our side lobes energies are in the decreasing fashion. So that is also correct. It's going and nullifying, I mean, keep on reducing its amplitude value towards pi is, omega is equal to pi radians. Correct? Guys, understood this rectangular window? Guys, understood this?
Yes, sir.
Yeah. Now we'll come to what after getting this rectangular function, how to get this h of n. Previously, h of n was defined simply h of n for duration minus n by 2 to plus n minus 1 by 2. But here we have to get h of n from hd of n by multiplying with the omega of n. Here rectangular function omega r. Sorry, w r of n. So this is the finite impulse response, we'll get it. Since hd of n is not known, we can get the same thing from h of e power j omega from this is equal to hd of e power j omega convolved with wr of e power j omega. This way also you can do. Okay, but this way is lengthy procedure. This way is a lengthy convolution, but there is a possibility to do it if it is a simple function. And when you do this multiplication hd of n with w or of n, h of n will be is finite values of samples. Here, because of this truncation, because of this small window values only we are considering in the h of n sequence, the response h of e power j omega will produce some oscillations in the pass band as well as stop band. So this kind of response you will get. Actually this ripples should not be present, but because of this abrupt truncage within the rectangular window, suddenly from zero values to some finite values we are changing it. There is a change. Suddenly we are removing these values. So we are losing some information. That will cause some oscillations about this ideal value. Okay. This phenomenon of getting ripples in the pass band and the stop band because of the abrupt truncation, this effect is called Gibbs phenomenon. Gibbs phenomenon. So this is a 2 marks question. They may ask what is the Gibbs phenomenon. So this will happen because of the abrupt truncation in the impulse response. The frequency response will produce some oscillations in the pass band and stop band. These ripples are due to this abrupt truncation. That phenomenon is called Gibbs phenomenon. Okay. Now, and see from this frequency response, we can also check what is the width of this lobe, central lobe. This width is minus 2 pi by n to 2 pi by n. This width is equal to 4 pi by n. Correct? So width of the central lobe is equal to 4 pi by n here. So remember this width of the central lobe. Therefore, we can compare with other windows how this rectangular window. I mean, in the properties we discussed is that central lobe must be very narrow. Therefore, the central lobe width will decide the transition band of the frequency response. Here, this transition band depends on that this 2 pi by n, 4 pi by n. When it is very small, this transition band will be very narrow. So this depends on that central lobe width. Okay, that's why remember that triangular window, as a rectangular window is having central lobe width of 4 pi by n. Now we will see the second window, that is triangular window. Guys, any doubt in the rectangular window, please ask me and get clarified now, because everything it's like a theory question. They'll ask to explain all the windows. So triangular window, triangular or Bartlett window. Triangular or Bartlett window. Now this window, this tapers smoothly. That means previously it was taken like this. No, it won't take like that. It will take like this. Triangular shape. Sample, 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 sample. This way. So this is a triangular shape. Okay. So this triangular shape will avoid the sudden change. It is not suddenly changing. See, it is smoothly changing. Slowly it is changing to the maximum value and slowly changing here also. So this is smooth tapering will avoid the ripples or reduce the ripples in the pass band and stop band of the frequency response. So we'll see how it is. The mathematical representation of this window is Wt of n is equal to 1 minus 2 into mod n divided by n minus 1. Okay, for minus of n minus 1 by 2 to n minus 1 by 2. Okay, right. And the frequency response of this triangular window Wt of e power j omega is equal to sine of n minus 1 by 4 omega divided by sine omega by 2 whole square. This is the frequency response. So when you draw this frequency response, you will get the response like this. Okay. See what happened here. This value is became 4 pi by n because of this. If you take it out, again you find if it is equal to and if you make it first whole square, then simplify it, you will get definitely here 4 pi by n in place of 2 pi by n in the previous case. You will get like this. Don't feel that I am drawing in a sharp way. Otherwise, better to I will redraw it. It is okay. So 4 pi by n, and this is 4 pi by n. So previously it was 2 pi by n, it is 4 pi by n now. Therefore, the width is equal to 8 pi by n. What happened here? The width is doubled. And but if you compare these side lobes, previously side lobes were more. Now see, the side lobes were reduced. Okay, the advantage of this triangular window is the side lobe heights are reduced, but the problem is the width is increased. So advantage is it side lobes are smaller. Side lobes are smaller compared to the rectangular window, and disadvantage is disadvantage is main lobe width is main lobe main lobe width is doubled. Main lobe width is doubled compared to the rectangular window. Okay, so because of this, the filter response, it may be like this. See here, the ripples are very minute and cannot be significant. Of course, these are significant based on the capital N value only. If you take N value very small, these ripples will be again significant. Whereas if you take N values more, you can't see these ripples in the pass band and stop band significantly. So basically, compared to rectangular, the ripples in the pass band and stop band are reduced. Okay, that's it. One second. Next, we'll go to third window. Right. Okay. Next, third window. What is the third window? Next is raised cosine window. Third one, raised cosine window. Raised cosine window. Raised cosine window, it is simply the multiplication of cosines. So raised cosine window multiplies the Fourier coefficients with the cosine. So it will further smoothen the curve. Here in the triangular window, it was sharp raise, right? But here it is a cosine shape in the sense it is a cosine shape. Like this. See, it is not a sharp raise. It is a cosine shape raise. That's it. I think you understand the difference. This raised cosine, we can denote it as W alpha of n, that is given by mathematically alpha plus 1 minus alpha into cos of 2 pi n divided by n minus 1. This is for minus of n minus 1 by 2 to n minus 1 by 2. Okay, So this is the window definition and its frequency response. W alpha of e power j omega is equal to if you solve this, you will get finally alpha into sine omega n by 2 divided by sine omega by 2 plus 1 minus alpha by 2 into sine of omega n by 2 minus pi n divided by n minus 1 divided by sine of omega by 2 minus pi by n minus 1 plus 1 minus alpha by 2 into sine of omega n by 2 plus pi n by n minus 1 divided by sine of omega by 2 minus omega by 2 plus pi by n minus 1. Okay, this is the frequency response of raised cosine window. Here alpha value we can set in different, you can select in different values. You can select different values so that we can get different types of cosine smooth variation here. And based on this raised cosine window, Hamming window and Hanning window, Blackman window are designed. So this next three windows are designed based on this raised cosine window. How much raise you can apply, that is deciding this window type. So next is the Hamming window. Hamming window. So Hamming window is obtained by substituting alpha is equal to 0.5 in the raised cosine window. Therefore, WHN Hamming window Hanning window. First we will see Hanning window. One second. Hamming window you can see directly. No issue. Hanning window. Sorry, it is Hanning window, not Hamming window. Hanning window, and here WHN Hanning window is equal to alpha is equal to 0.5. So 0.5 in the previous formula. 0.5 plus 1 minus 0.5, that will give again 0.5. 0.5 cos 2 pi n by n minus 1 for minus of n minus 1 by 2 to n minus 1 by 2. And the frequency response of this Hanning window WHN of e power j omega is equal to 0.5 sine omega n by 2 divided by sine omega by 2 plus 0.25 sine, same frequency response, alpha value we are substituting as 0.5. That's it. Omega n by 2 minus pi n divided by n minus 1 by sine of omega by 2 minus pi by n minus 1 plus 0.25 into sine of omega n by 2 plus pi n by n minus 1 divided by sine of omega by 2 plus pi by n minus 1. Okay, and here this handing window is shown like this. See this is same as the raising cosine window, but based on this variation, alpha value will be depending on. This is handing window, WHN of n. Okay. And its frequency response is okay. See, this value is 4 pi by n. If we calculate, it is also 4 pi by n for this handing window, WHN of e power j omega mod. So its width is again 8 pi by n, same as the triangular window. So transition bandwidth is not changed, it is still same, but here these ripples are further reduced compared to the triangular window. That is the advantage of this handing window. And next is Hamming window. Here Hamming window is same as the raised cosine window. Hamming window is the fifth one. Hamming window is same as the raised cosine window, but the difference is alpha is equal to 0.54 will substitute. Therefore, WH of n, H only H means Hamming window, HN is the handing window. Remember this point. So it is equal to alpha is equal to 0.54 is substituted, is equal to 1 minus 0.54 is equal to 0.46 into cos of 2 pi n by n minus 1 for minus of n minus 1 by 2 to n minus 1 by 2. Okay. This is the Hamming window mathematical expression, and its frequency response is given by 0.54 sine omega n by 2 by sine omega by 2 plus 0.23 into sine of omega n by 2 minus pi n by n minus 1 divided by sine of omega by 2 minus pi by n minus 1 plus 0.23 into sine of omega n by 2 plus pi n by n minus 1 by sine of omega by 2 minus plus pi by n minus 1. Okay, and this mathematical graphical representation is compared to the Hamming window, this is having little bit difference. Otherwise, the rest is same only. See, it is done like this. Of course, this height is more. So this is a Hamming window, WH of n, and the frequency response is it is see it's a very small these ripples. So side lobes are already almost negligible, and but unfortunately the main lobe width is not changed. Same, but ripples are still reduced. That is the Hamming window. And next is the Blackman window. Next is Blackman window, sixth one. Blackman window. So Blackman window is defined as WB of n is equal to 0.42 plus 0.5 cos of 2 pi n by n minus 1. Here alpha is not fixed. For this it is 0.42. Here it is not 1 minus alpha. Here it is 0.5. These coefficients are different, but pattern is similar to the raised cosine function. And added one more 0. This is splitted 0.08 cos of 4 pi n by n minus 1. See this and this combinedly giving 0.5, and this 0.5 is as it is. This is for minus of n minus 1 by 2 to n minus 1 by 2. Okay. Here the frequency response is similar to that, but the coefficients are different. But the thing is the frequency response of this filter this is the window, and its frequency response will be giving still still no ripples in the pass band and stop band, but thing is the width is increased. So it is minus 6 pi by n2 plus 6 pi by n because of extra term is added now class. So the width is increased. Therefore, the total width is 12 pi by n for Blackman window. That is the difference. And next and last one, in order to reduce this main lobe width and reduce the ripples are reducing by window, but thing is the width is increasing only, not reducing. Width is best in the rectangular window, but the side lobes are reduced in the Blackman window. Means from a triangular window to raised cosine window, Hamming window to Blackman window, it is still reduced ripples. So in order to provide both the advantages together, we have the next option that is called Kaiser window. Kaiser window. This clubs all the window advantages. Then the mathematical expression also, the mixture of all. So it is defined as mathematical relation of this Kaiser window. Wk of n is given by I naught of alpha into root of 1 minus 2n by n minus 1 whole square divided by I naught of alpha for mod n less than or equal to n minus 1 by 2. Okay, where alpha is an adjustable parameter. This alpha, where alpha is an adjustable parameter. And this is I naught of x, where I naught of x is a zeroth order Bessel function. Zeroth order Bessel function of the first order kind. Bessel function of first kind of order. First kind of order 0. First kind already written this zeroth order. Again not required. And this I naught of x is given by 1 plus summation k is equal to 1 to infinity 1 by k factorial into x by 2 whole power k whole square. Okay, from this we can find out the Kaiser window Wk of n. Here I naught of this total, first we will find out this value, and for this value I naught of that x, if you place here x value, you can find out I naught of that value. That way we can find out the samples of Wk of n. It's looking complex only, but calculation is more. Apart that, everything is okay, normal. Once you get the window values sample, then easily further you can multiply with ht of n, you can get h of n, and remaining procedure is similar to the previous problems. So only the difference is these formulas are looking different and complex. Okay. And this Kaiser window frequency response is given by Wk of e power j omega is approximately equal to 2 by I naught of alpha into sine of n minus 1 by 2 into omega square minus 2 alpha by n minus 1 whole square under root divided by omega square minus 2 alpha by n minus 1 whole square under root. Okay. So in this, if you substitute alpha is equal to 0, you will get this is equal to rectangular window. Kaiser window is equal to rectangular window. Substitute alpha is equal to 0, this will be 0, this will be 0. So what you will get? Omega into n minus 1 by 2, here omega by 2, here omega. So under this, if you calculate, you will get similar to the similar frequency response to that of the rectangular window. And suppose if you substitute alpha is equal to 5.1414, then this Kaiser window is equal to Hamming window. You can test it, can try. And next, if alpha is equal to 8.885, then the Kaiser window is equal to Blackman window. Okay, Kaiser window is equal to Blackman window. That means from these different K values, alpha values, we can achieve different functionalities, different windows. So easily you can tune it. This based on your application, you can tune the alpha value and you can achieve your required or desired window.